I think it is already. Thanks.
Our speaker today is Victor Maluleke, who currently works with a company called Enviro Excellence and coordinating projects for groundwater monitoring, drilling and siting supervision, and borehole pump testing analysis. He has a degree in geology from the University of Limpopo, an honours degree in hydrogeology from the University of Free State, and is currently doing his MSc in geohydrology with the Institute for Groundwater Studies at the University of Free State. Today, Victor's talking to us about the investigation of the influence of groundwater abstraction on surface water levels and surface water-groundwater interaction in a South African context. And with that, I'm going to hand you over to Victor.
Thank you very much, Noling, and the GSSA team. And thank you very much also for the GSSA mentoring program for actually giving us this platform to come and give the talk. Here with me, I have my progress. I'm actually currently doing my master's, as Noling said, and I'm going to sort of like brief outline the research that I'm currently doing, although I don't have my data that I can show you. Because of the challenges of COVID, I couldn't go to the site and sort of like collect the data. So, but this is now where me and my supervisor will be going to the field. So hopefully next year we will be coming back with the field with the data, and then I will be able to show you the data as well as the modeling part of it. So. This is actually my declaration that this is actually my own work, and it hasn't actually been presented to any institution as well. So the brief outline of my presentation, I'm just going to brief you with the introduction, the background study of why actually I'm doing this research, and just to give you a bit basic literature on the field, the researchers that on past they've been doing this research, and actually just to take you through. And at the end, I hope you will be able to appreciate the concept of surface water groundwater interaction in a way. And I'm just going to give you the way forward as well on my dissertation on where to from here after presenting my dissertation as well. So the acronyms that you will be able to encounter in this presentation is the following is just the GSW, which is going to be the groundwater surface water interaction, and the NWA, which is like a National Water Act. So these are the acronyms that one will get as the presentation go through. So the aim of my dissertation as well is just the investigating the groundwater surface water interaction and the impact of groundwater pumping. In a way, I've included over abstraction, and I'll just explain a bit later on why it's actually over abstraction as in well. And then this is the investigation of groundwater surface water interaction and the impact of groundwater pumping on surface water body. And the objective of my dissertation is to investigate groundwater and surface water abstraction, or investigating groundwater and surface water interaction. And in this case, it's just to access or assess the interaction between the groundwater and the aquifer in surface water bodies. And the following aspects will be addressed, and I've been addressing in my dissertation, which will be the location of the site specific. In this case, I haven't done my site specific investigation because due to the lockdown, we haven't been able to go to the field as well. So these are some of the things that we'll be doing as my dissertation proceeds. And also the investigation and investigating and improving the understanding of surface water and groundwater interaction and the effect that this groundwater abstraction has on surface water. So for us to understand the groundwater and surface water interaction as a whole, we must also understand and just improve the knowledge that has been there to be able to understand this groundwater and surface water interaction. And the other one is just to go to the field as well and collect the data and come back and do the evaluation of modeling approaches to just quantify these effects of groundwater abstraction. And then by then we'll just be able to recommend the modeling tools to quantify these effects of groundwater abstraction on surface water. So just to give you the overview of groundwater abstraction, groundwater surface water interaction, sorry. It's very important that when we do the informed decision on water management, you must actually understand and learn to appreciate the fact that it is important to know the key fundamental behavior and characteristic of surface water and groundwater interaction, so that we may be able to support this informed decision on water management. So we can't do the water management before we understand the basics, which are the behavior and the characteristic of surface water and groundwater interactions. So the interaction between the two, it's actually important to note that it's not through throughout the whole world, but also in South Africa, it is actually a concept that remains poorly understood. But it's important to the researchers that it is actually a fundamental importance. It's of fundamental importance in managing and the quantity and the quality of water resource. So as much as this actually it's poorly understood in many catchments throughout the world, it's actually of fundamental importance in managing the quantity and the quality of water resource. So this is actually the point that I will actually explain further in my diagram, that the groundwater is commonly actually discharged to the stream. And this is actually a concept of base flow, but I won't go through the concept of base flow now because of time, but we have to learn to appreciate that groundwater is commonly discharged to a stream. And this is actually my focus of my dissertation, to say, how are these two, the groundwater and the stream, are actually interlinked? How is the connection between the two? And if there's a connection and this connection is there, and we are proving that is there, then what is actually the effect of groundwater as we're abstracting on the rivers or surface water bodies? So this is actually the diagram that I've been saying in there, to say the groundwater is actually commonly discharged to a stream. You can actually see here in my diagram that there's actually a recharge, and there's a recharge. It's actually water is actually recharged maybe from rain or other source of water, and it's actually recharged to the unsaturated zone, which in this case, this part is actually my unconfined aquifer. Is recharged through the water table, and this is actually my recharge source. So eventually, it depends on the time, it depends on the scale, depends on the groundwater flow path movement, it will be recharged either into the stream, and this may take days, may take years, may take centuries or millennia, depending on the permeability of materials, the movement of the groundwater flow to the discharge area, and also it might be discharged either into the pumping well as well through the discharge of our groundwater. Our groundwater is actually discharged through the pumping well as we pump our water out via the pumping well. So as you check here, you might be asking yourself why days here. So it actually plays a factor as a resident time, because the groundwater as well, it moves along the our permeability zones. It moves along the permeability materials, and this might even take years to reach to the discharge area, and it might, these confining layers as well might even play a role in groundwater flow path as well. And it might even take days if it's actually closer to the discharge source. It might take years if it is actually far away from the discharge source as well. And the movement is actually interlinked with the permeability material. I think I will actually explain a bit further about that. So as I move on, and I've said this, it moves continuously through the aquifer. It moves through the aquifer and the discharge to the discharge source. And this it varies. The movement might varies from travel distance to travel time as well. It might varies from few kilometers to few meters to the discharge source. So we must learn to appreciate that in groundwater surface water interaction, it's not about focusing on the local areas, but focusing on the large areas in the catchment, because sometimes we deal with the catchment, and we must learn to appreciate as well that if we are dealing with a groundwater that is discharged from somewhere else, it might take years to come to the discharge source. If it is discharged to an area of far focus, it might actually it will actually eventually at some point reach to the area of discharge, but it might take years to become evident in such area. So, and also that in this point that I have here, the discharge can range from days to few years to millennia, depending on the permeability of material. And I feel like I've explained that a bit earlier on, that the permeability of material, it actually plays a role in the travel or groundwater flow path as well. So as I continue as well in figure 2, we'll learn to appreciate as well that there's a category, or it's actually categorized. The groundwater flow scale is actually categorized into a local and sublocal regional scales as well. So I will actually explain that few further later on in my diagram. So it's actually important as well that when we focus on the concept of groundwater surface water interaction, the focus on the borehole, which is actually they actually focus on the close proximity with the surface water. So when we do the concept of groundwater surface water interaction, most research will focus their research on like a local based area, because due to lack of data in this field, is very much difficult for one to sort of like look at the whole catchment in an area because of lack of data. But despite that lack of data, managers should actually keep in mind that surface water receive water from both local and regional and sub-regional scale system. So it is important that as much as we are working with a proximity or close proximity with the surface water body, we must actually factor as well a key fundamental to keep in mind that also the surface water can get this groundwater discharge from various scale system, which is maybe can be local, regional, or sub-regional scale as well. And it is important also note that it is not always the case that groundwater abstraction may always be adjacent to the surface water. Groundwater abstraction as a source, maybe a borehole might not always be adjacent to the river. In a case, maybe a river might be far, a borehole might be far away from the river. But in that case, it can be a point that as we abstract in that borehole, it can affect surface water. But it is important to also note that evidence might take years to become evident. That impact might take years to become evident, even though the borehole is not actually adjacent to the river. So it is actually important that one might actually keep in mind as we are busy with this concept of groundwater surface water interaction. And as I've said, it's based on local, sublocal, and regional system scale. And this is actually a groundwater flow system or flow scale system, where now we have number one here as our local groundwater system. And this is actually a recharge in this area where you have your recharge here, and it's closer to the discharge source, and it might take days, this one, to come to the discharge source. It might not take years, but it could take days to come to the discharge source. But if you check number 2 here, I don't know if you can see my arrow point. So number 2 here, you have your sub-regional groundwater system or subsystem as well, where this one might take years to become evident as well, due to the sub-regional scale system. It might be recharged somewhere far away from the discharge source, and it might travel along the system or groundwater flow path and take maybe years to come to the discharge source. And as well, we have a regional groundwater subsystem as well, where in this case it can depend also on the permeability of material. It moves along to your confined aquifer. It moves along to the different varying aquifers until it reaches to your discharge point. So it is actually important that once we understand this groundwater surface water interaction, we have to factor out as well the groundwater flow system as such. And then once we move further, the groundwater interaction in the streams are dominant point of interaction. And this is actually my point of focus in my research, because as we are factoring out groundwater and surface water as a part of interaction, it's very important that we must note that these two resources actually a dominant point of interaction in terms of water resource management. And the stream reaches itself, as I explained further, the dominant point. The stream reaches itself, it can either receive water from the groundwater discharge, and this concept is called gaining stream, or it can either loses water to the underlying aquifer as well through the stream bed. And this concept is actually called losing stream, and I will explain that bit further. And then the rate that controls this movement, either receiving water, either stream receiving water from groundwater, or either it loses water to the underlying aquifer. It actually is actually from this point to say that the aquifer can be connected to the surface water. Either can be the hydraulic gradient or stream bed material, or either it can be geohydrological or geologic material as well, that can be located within the interface of groundwater and surface water as such. So it is actually important that these factors are actually in back of our minds to say that as we talk about the rate that controls the movement of water from stream to the connected aquifer, we must factor in the hydraulic gradient as a factor. We must factor in the stream bed material as well, and the groundwater geologic material as well in these systems. So this is what I was saying about the gaining and the losing stream. So if you check here, we have a water table that is actually higher than the river stage, and in this case, if you check the concept of groundwater, it follows the topography. So if you check, this water table is actually higher than the river stage. So automatically, in this case, conceptually, so the water, groundwater, will actually feed to the stream, and in this case, it's going to be the gaining stream in this case. But in this case, on your right, your water table is actually lower than the river stage in this case, and obviously, in this case, you will have your river that is actually losing water to the groundwater. So it is actually important that once as well we are talking about the groundwater surface water interaction, we have to factor in mind the fundamentals of gaining and losing stream. So we can't talk about groundwater surface water interaction if we don't know the basics, behavior, and the characteristics of how they are actually interlinked. And then I bring to you the stream flow reduction or depletion. So I've put this as a reduction or depletion because at some point, some articles out there, these terms, they're actually interlinked. They're used interchangeably. So sometimes they use reduction as part of deforestation, I think, and some other part they use depletion because now people are actually abstracting the bowl at some point, and then there's a river, and then they're actually altering the river. So they use it as a stream flow depletion, although it's actually debatable that these two concepts are actually similar, or maybe they can be used differently on different purposes as well. But the points that I want to bring to you is that the stream flow depletion has become a very, very much important water resource management issue because of the negative impact it has on the aquatic ecosystem and the quantity and the quality of streams and rivers as well. So we talk about the river depletion, we talk about it as an important resource in water management because of the negative impact it can have on the ecosystem and the quality of the stream and rivers. And it involves two processes in both gaining and losing stream. I think now we know what is both gaining and the losing stream. So this stream depletion, as I move towards the concept of my research, which is actually the stream depletion as well, it involves two processes. These two processes, I've actually incorporated them into my diagram here, where you can have your bowl here, and you have the adjacent stream as well. So this is actually a conceptual, diagram where you can have your bowl here, and then you have your river somewhere there, and then as your river, as you pump water, the hypothetically this is actually an unconfined aquifer. So as you pump water, it may be large enough. So sometimes it might be large enough that you pump water that it will even cause the groundwater to flow from stream to aquifer. So in this case, you are actually altering groundwater that was actually supposed to flow to the river, and it comes and it's actually captured to the well. This automatically eventually can cause stream flow depletion. And this is actually a concept of induced filtration. I won't go further much on that concept due to time. And the second process that is there is that you have your bowl as well. You also have the adjacent river as well here. And then as you pump water, you have your cone of depression that is actually extending outwards. So once you pump water, you have your cone of depression that is actually will be extending outwards from the pumping well, and the well will actually capture groundwater that would have been supposed to be discharged to the stream, coming to the groundwater, and you discharge them, and eventually you will actually tamper with the stream, and then the stream will actually be depleted in such. So one might ask himself or herself that what is actually the factors that actually affect the stream flow depletion? But first, before we go there, we have to learn to appreciate the fact that stream flow depletion can actually vary over time. It might be a period where now you have your stream flow depletion that is actually depleted rapidly, so, or it's a factor, or it's a concept that maybe you have a stream flow that is actually being depleted, but it's a delayed response process in years or decades. So we must actually learn to appreciate the fact that we have your stream flow depletion that is actually depleted, maybe due over time, or it may be a repeat process, or maybe it is actually delayed in years or decades. So the factors that actually affect the stream flow depletion in this case, it might be either a groundwater abstraction, or when you over abstract water, then you have your stream flow depletion. It might be horizontal or vertical distance of well to the stream. I feel like I will just explain a few points of on the next slide as well. So we have also the hydraulic parameters of the aquifer. In this case, we talk of transmissivity, we talk of storativity, and we talk of also the permeability of a stream bed. So all these factors, they can affect the stream depletion, but it is not like a one factor that maybe like groundwater abstraction can affect stream flow depletion. It is all these factors that can affect stream flow depletion. So if you have your permeability of a stream bed, for example, and you have your groundwater over abstraction, you have your hydraulic parameters, you have horizontal, vertical distance, then you can factor this and quantify this and check how are these actually affecting your surface water inside. So this is the table that I was actually trying to sort of like summarize all these effects, although maybe there are other factors as well, but these are the key fundamental factors that one should understand before going to the field and try to quantify this in a model. So you can have your pumping rates as for example. Then it is important to note that as large pumping rate occurs, then obviously the stream flow depletion will occur. So as much as you are pumping more water in a bowl that is actually adjacent to the river, then obviously it can happen that you have a stream flow depletion inside, if these two are actually connected. So there's a literature that says they are putting typical ranges that are actually likely to cause stream flow depletion. And this year they said it's about 100 to 10,000. And they said if it's actually less than 100 meter cubed per day, that is actually unlikely for you to cause stream flow depletion. So if you abstract water less than 100 meter cubed per day, it's actually unlikely to cause depletion in stream flow. But otherwise, this is actually it's actually also debatable, because you can say, yes, in the literature there's values that are put in place, but it actually differs in a site specific, in a point that you have to factor out all these your parameters that are actually influencing this groundwater abstraction as well, or this stream flow depletion as well. So the source of data that you can find these pumping rates, you can find them in your direct measurements from pump testing or abstraction well. And number two, you can have your separation distance as part of the factor that can affect stream flow depletion. And this is when you have your bowl that is actually far away, close or closer to the river as well, or the surface water body. And in the effect, it says that the small separation or the small separation can increase stream flow depletion. So if you have your bowl that is closer to the river, this may increases the chance of stream flow depletion. And the typical value they've put like is about 1 to 2,000 meters distance. So this is a sort of like a buffer zone or cutoff zone. And the distance from well to nearby, if it's actually greater than 2,000, so it is actually unlikely to cause stream flow depletion. So if you have a bowl that is actually greater than 2,000 meters, that is far away by 2,000, greater than 2,000 meters from the stream or the surface water body, that is actually unlikely to cause stream flow depletion. And I can still say that these values are the values that are still debatable. I mean, science is something that you can actually you can debate. It's debatable. Values are not constants. You can say it's greater than 2,000. You have a bowl that is greater than 2,000, but hypothetically it's like that. But we can still come up with some values. And I feel like this research of mine is actually also being motivated by that I feel like I'm going out there to come up with values as well that suits site specific, to say, okay, if I have my bowl that is actually greater than 2,000, can it affect the stream flow depletion as well? So these are the values that are in literature, but I feel like it doesn't mean that these values are there to say that in all these places or in all these site specific conceptualization it can work. It might work in other areas, but it doesn't work in other areas as well. So we might actually factor this in our mind. So the source of data that we can find this separation distance, it can be from topographical map, it can be from aerial photograph, it can be from direct measurement. And this source of data will then help us to go and collect data and come back and do our modeling. So these are the source of data that we can find our data as well. So number 3, we can have our pumping period as well, and this is the source of data that we can find our measurements as well. We can either measure it, we can either also go to the from industrial requirements or irrigation system. That's where we can find our data from pumping report. And number 4, we can have our transmissivity, and a transmissivity, as stream flow depletion increases with high value, and stream flow depletion increases with high value of transmissivity. So as transmissivity increases, transmissivity is a concept where you have your the transmission of water through the unit length of an aquifer. So if you have your high transmissivity, there's high chances of stream flow depletion. So we must actually keep in mind that these factors are interchangeably. You use them, all of them. Not one factor can actually affect the stream flow depletion. And the source of data can be from the pumping test data or the slag test. So these are the geohydrological terms where maybe you can get this data from the transmissivity data from, if you want to do your modeling and you check how are these factors actually affecting the stream flow depletion as well. So number 5, you have your storativity as well. And the storativity, it means that the literature is saying that if you have your low storativity, it means that it is actually confined aquifer, because confined aquifer they are involved in low storativity. It is actually likely that you have your stream flow depletion increases in low storativity, which is actually greater than 0.0005, and this is actually low storativity in such. But it's actually unlikely for you to actually have this confined aquifer connected to stream, unless the stream is actually penetrated to confining layer. I think you've actually seen in the previous diagrams where you have your stream and a confining layer. So when you go to the field, sometimes we have to factor in out when you are doing a modeling that, are we dealing with a confining aquifer? Are we dealing with unconfined aquifer? So that when we do our modeling, it should speak well with the site specific we chose. So the source of data that we can find in this, it can be either the test data with observation well, or if we don't have the test data, we can use it as an assumption that we are working with an unconfined aquifer, which S will be maybe 0.1, and then that's when it will be applicable when we do our modeling. And then the stream conductance as well as as the last point that I'm the last factor that I'm talking about is going to be the stream conductance. So the stream conductance, it can be the range, typical value range from 0.01 to 5,000 meters per day. Like I said, these are the values that have been put in the literature, but still one can go to the site and try to find other values that can suit the site specific. So, large values greater than 5,000 as well. It means that you have your high stream hydraulic conductance, and this can cause the stream bed to stream, in a way, stream depletion to increase. But it is very unlikely that the stream depletion will occur when the stream conductance is actually less than 0.01. So the source of data, it can be from the seepage meter or from the infiltration side. So if you want to find the stream conductance data, you can find them from seepage meter or the infiltration test. And then it won't be complete enough if I don't talk about the legislator or what is the South African legislation is saying in the stream flow depletion. So under the National Water Act, based on the 28th principle, water management is actually regarded as invisible. Why? Because there's no distinction between abstraction from the river, especially when there's no connection between the groundwater and the surface water. So it is very important, and it's up to us as geohydrologists to actually go to the field and do a proper geohydrological study or hydrological study, and it's actually to then indicate whether that there will be an impact or the impact will exist in that system. And if there's a risk and the risk is actually unacceptable, then we'll have to find a proper mitigation measure to actually prevent the risk from occurring. And it's very redundant to actually come up with a buffer zone as a mitigation measure to say, no, this will work as part of water governance approach, because the impact and the system depend on the site specific. I can't say, okay, I have a bowl. If we drill bowl greater than 2,000 meters, then it won't cause any effect in our stream, because that 2,000 might work in a system or in other system or in other areas, but it won't work in other areas because geology is different. So that's why I'm saying the buffer zone is a bit redundant when it comes to water governance approach, because we can't factor say, okay, this is our the buffer zone for 500, we can use 500 in all South Africa, because it's such, if we don't have the basic idea of saying why is the stream flow depletion occurring in that area, what is the geological characteristics and the behavior in that area, then we'll have to come up with a perfect buffer zone in that area as well. So this brings me about to my modeling groundwater surface water interaction. Just to give you a basic idea, the coupling of this surface water and groundwater interaction can be done through both analytical or rather numerical model. And the quantifying of this stream flow depletion may ranges from easy to cost-effective analytical model to more complex and detailed numerical model. So when you talk about the analytical model, it's very important because it gains insight into the system behavior and it estimates depletion under idealized condition. So this, in this case, we sort of like represent our system into a very idealized condition. So we actually have the simplified representation of a system. But when we go to the numerical model, we talk of them, it's actually more popular than the analytical model, because in this case, it is actually able to actually handle many geological complexity, especially in the catchment scale. This geological complexity, they are very important because they affect the timing of the stream flow depletion. So we have to factor out this geological complexity when we do our investigation, because it can factor out the stream flow or the timing of the stream flow depletion. And this complexity might include non-uniform soil. These are the things that are actually found in the real world system. So we can find the non-uniform soil, we can find the, you know, the different stream geometry, the non-idealized aquifer geometry as well. So these are the factors that we have to use in a numerical model system when the analytical model is actually limited, because we can't use analytical model in such hydrological or geological complexity. So the challenges in our models when we do the modeling of groundwater interaction is the different in time scale. As we know that the groundwater flow is magnitude slower than the surface water. So there's a bit of lagging in time response for groundwater pumping to our stream flow depletion. So it's very important that when we do our groundwater models, we factor in these time lags in our models, so that we might be able to capture easily the response of groundwater pumping to our stream flow depletion as well. So the analytical model, just to reiterate that the concept, is actually based on the estimation of simplified approaches. And this is what I've been saying. It can either be a single well. When you have a single well system, I will explain just a bit further in the diagram. You have your simplified representation of a real world, and you provide, and in this you provide a quick estimation of stream flow depletion by nearby stream to a pumping well. And it's very easier to use the analytical model, and it's easier to implement on the spreadsheets. Their equations are user-friendly, and user-friendly softwares are available, and also they require less specific data to use than the numerical model, because in this case you are dealing with a simplified representation of a real world. So obviously you will require less data to model such effects or such impacts. And then it is very important to note that it is not only simple, it's not only the simple model, or it's not actually simplified only, but other researchers out there, they've improved this conceptual model to of stream aquifer and well system. And this is what I'm saying. The simple conceptual or the simple conceptualization of stream aquifer and well system is that you will have your, this is actually, it's I don't know, it's actually very difficult, or rather it's not even very possible for you to can find in the field. Just a straight line river with one well that is there, and then you can use to the field. But you will learn to appreciate that as you move from analytical model, you try to build your conceptual model and try to understand and gain insight into our system, so that you can move further to our numerical model and try to even gain more insight into our system. So here you have your global model is trying to explain that, okay, you have your hypothetical aquifer stream conceptualization where you have your well and your system, and then as you pump your well, how does it affect your river inside? So here you have your boundary conditions that are well defined, and this is actually very impossible that you can just find in the field, where you have your boundary conditions that are actually well defined. So And in other case, the analytical model can be a bit improved into a real, just to imitate the real world system, where you have your, now the factor of a stream bed. This is a stream bed sediments, where now we have mentioned earlier on that the factors that can affect the stream flow depletion, one of them is the stream bed sediment. So in this case, Antush model is actually coming into place, where they are actually factoring in the stream bed sediments as well, and this can be can play a very big role into stream flow depletion as well. So in the numerical model as well, we have this is actually the powerful tool into getting insight to a system behavior, as I've said, because it actually estimates the stream flow depletion into idealized condition. So it addresses the complex factors that can have the substantial effects on the stream flow depletion that can limit the use of analytical tool. So where the analytical tool is actually limited, then that's when the numerical tool will come into place to address the more complex factor. This might be multiple well pumping simultaneously. It can be irregular aquifer dimension as well. It can be irregular geometry of the stream and variable surface water features, such as meandering stream. And this is the factors that analytical tool or analytical solutions might be difficult to factor in. And this is when numerical model come into place, because they are able to also factor in the heterogeneous aquifer properties with varying parameters as well, and the time varied pumping schedules. So if you're pumping seasonal pumping schedules, you're pumping today, tomorrow you're not pumping, pump day after. So it is actually able to factor in such timing varying pumping schedules. It's also important as well to factor in irregular sources that are actually not constant over time. So this is a concept of transient solution. So we are able to also model the transient solutions in our model as well. So also the difference in boundary conditions at a different scale. So this is what I was saying. This is actually the hypothetical representation of a stream aquifer system with a finite difference model. So you have this black thing. This is actually your boundary conditions that are actually different in time and scale. So it's not like one straight boundary condition as we have seen in the analytical solution. It's not like a one straight river. This is actually a river that is having a tributaries. It's not like a one well. This is actually multiple wave. You have one multiple well, and numerical model is tried now to actually incorporate things that are actually in the field, that you can see in the field, that analytical model might find it harder to even incorporate. So just to conclude, my way forward on my research, like I said, it was going to be nice to come with the data in the field that I've collected, try to show you how I've tried to model these factors of stream flow depletion, where I have a well, when I have a scenario of a well, where I have scenario of tributaries as well. But due to COVID-19 that affected my research but now, because now we have easy there's some easy in lockdown, then we'll be able to go back to the university and sort of like collect data and try to come back. Hopefully next year I'll be coming back to you with guys to just show you perfect examples that I've did in my model. So yeah, I think you will learn to actually appreciate that at least there's an basic idea and a basic overview of surface water and groundwater interaction, and how we factor in this surface water, the stream flow depletion, when we have groundwater discharge or groundwater over abstraction as well. So thank you a lot. Thanks a lot.
Thank you so much. Do we have any questions for Victor or comments? Anything? Well, Victor, you were obviously very clear. Everybody understands what you were saying.
Thanks a lot. Thanks a lot.
Victor, maybe one question from me. Are you at liberty to divulge the location of your field studies?
Currently, I'm actually a bit struggling as well with finding a suitable site for my field, because for example, in terms of funding as well, but and also like availability of data. But at the moment, I haven't. I don't have like a site, suitable site specific that I can. So this is my study area that I can do my research on. But you know, and in such, I think I will be working on it. I've been working on it as well.
Hello.
Hello.
My name is Crystal Lowe. I'm from the Department of Water and Sanitation in the Northern Cape. I just would like to thank Victor for his incisive presentation that he offered to us. It's linking also to my topic that I'm currently busy with. I'm also having challenges with getting data to do the studies that I want to do, because obviously I'm following the approach as the custodian of the department. My topic is mostly related to identifying practical approaches for setting resource-directed measures for groundwater through corrected groundwater resource control measures applicable to various water use authorizations. But the challenges that I'm faced with is with respect to confidentiality clauses that are stated and getting access from the department. Like for instance, WARMS information that's normally the registry on the water users, and as well as the water management system where they normally load the water quality information. But I actually like the approach that he has followed. I was actually hoping you would be able to provide me with some hints as to how can I also go about collecting information to do my studies.
Okay, thanks a lot.
Yeah, okay. So do you need some more clarity?
Anybody want to take this? I think, Christo, maybe just drop me a mail and we can take this further and discuss it further. I just mailed you earlier, so you do have my email address.
Can you just provide... Oh, okay. Thank you so much.
Okay,
I'll
sure.
drop you an email earlier. I mean later on. Okay,
that's fine.
you.
Thanks, Christo.
Bye-bye.
Okay, bye. Are there any other questions or comments? Okay. I think in that case, we'll end today's meeting. Thank you so much for joining us. It was a really interesting talk. Thanks, Victor. And as Victor did say, it is part of his mentorship program with the GSSA. So if there's nothing else, Craig, if you don't mind closing the meeting for us.
Thanks very much, Nolene. Thanks, Victor. I'll close the meeting for everybody now. Thank you all.
Bye.
But